Good afternoon. Well, thank you for your attention in the last presentation. So my PhD is an industrial PhD done between IPVF, total energies, and the CNRS. And the topic is the degradation mechanisms of solar perovskite solar cells and mini modules with the aim of developing methodologies and phenomenological models of what is happening. So this is the general context. We have this technology that is trying to compete in the future with silicon devices. And this device, this solar device, have different kinds of materials, like a hybrid between organic and inorganic, fully organic or fully inorganic. So it's exposed to different kinds of degradation elements, like extrinsic, moisture, oxygen, but also intrinsic regarding the operation of the device, like the temperature, the extraction of charge, etc., the illumination intensity. So the idea is to investigate what are those kind of degradation mechanisms closer to the real operation, so in the full stack device, and with different kind of architectures. So we have different compositions developed at IPVF. And how we plan to do that? Well, first we have a set of methodologies that are quite agreed in the between different laboratories. The ISOs, so-called ISOs protocols that apply different conditions like dark, light, oxygen, outdoor, thermal, and cycling tests, and accelerate the degradation to see what are the different responses of the devices. After we follow these mechanisms with these protocols, we try to elaborate some models, and we use some complementary techniques to corroborate the changes, for instance, chemical changes on the perovskite absorber or at the interfaces or migrating elements. So this is the general context, and now let's go to some examples, some results. Here is some devices that were fabricated for the we call it impact, the fabrication team at IPVF. So we have 3 sets of different architectures, and we have the classical current voltage characterization. Each color is a different light intensity. So we illuminate the device and we extract the current voltage response. We see different features on the operation. For instance, some barriers, some formation barriers, like what we call S-shape formation, depending on the light intensity. That there are some hypotheses that, for instance, is related with a poor operating transport layer. So one of the layers that is used for the selective charge extraction might not work properly. So what we are trying to propose to better understand what are the degradation mechanisms of the device is one of these techniques is impedance spectroscopy. In impedance spectroscopy, we are playing with the frequency. So we basically do the same characterization of current voltage at different points of the operation, and we play with different frequencies. So we get resistive and capacitive components that, depending on the frequency, give different meanings. So if it's very high frequency, it's telling a response that is related with the contacts or with the perovskite absorber layer, or into very slow processes at the interfaces. For instance, if we have migrating elements that are polarizing the interfaces, we can see at different timescales. And those different phenomena give different shapes on the impedance plots. So each semicircle, I call semicircles, each semicircle is a different phenomena. What we have here is a physical explanation of those different phenomena through an equivalent circuit. So continuing with the examples, we have done this technique at IPVF. We see 2 different devices and how the characteristic responses are slightly different between them. And one thing that we are doing lately is we are trying to reproduce that experimental results into simulations. So creating a digital twin of the device. And with this, we can better correlate the real response with the specific properties of each material. So mobility, of each layer, ion concentration, etc. And the complementary techniques that go after is, for instance, if once we have some hypotheses, we try to corroborate with this complementary characterization. So we have photoluminescence, we have XPS. So for instance, in XPS, we try to see the elements. If we have some elements that were volatilizing, escaping from the device, or migrating towards one interface, we try to observe it with the XPS. Also, we have some mechanical issues. Here you see two electron microscope images of the stack with the different materials, layers, like a sandwich. And we have some mechanical issues, for instance, delamination, like separation between two layers inside the stack. So yes, we are trying to create a methodological analysis that combines different techniques to give an holistic response on the degradation models. And this is the last example. This is like the last step that we are implementing. We are doing a accelerated degradation test on the devices. In this example, we do a light soaking test, two architectures here for 900 hours. And what we see is the power loss of the devices. Here you have the IB curves of each device when it's fresh and then degraded. And we are trying to explain why the IB curves are changing by doing also impedance spectroscopy and observing how each resistive and capacitive element change on the device. This is an offline measurement, so it means it was measured at the beginning once and then at the end. So the upgrade is to do the online in situ characterization, that we are following the degradation, the power loss, at the same time that we are doing the impedance. And for that, we are building this interconnection system where we have the classical climatic chamber where we place all our samples, all our cells, the measurement unit for the power loss, the IB curves, and a new setup that is interconnected with the other two. So we need a controlling system here that is switching between the IB tracker and the impedance characterization system. So yes, that's all. Thank you for your attention.